All right, here we go. We're going to do part 2 of this module on transformations of linear functions. And so we did a translation before we moved up and down the vertical axes, or went left or right the vertical axes. Now we're going to dilate. If you think about dilation, you probably had your eyeballs dilated when you went to the eye doctor, or there was the I always say I'll call it the Men in Black, but Men in Black, one of the characters, I think the guy was really, really fast that Will Smith had to catch. His eyes dilated. It dilated weirdly. It dilated to the sides, but they dilated. Cats' eyes will dilate. Okay, so when I'm looking at dilation, it's the same kind of a thing-ish in terms of the definition of it. So it's going to either stretch or compress the graph of a function. So when we think of stretch or compress, you think like, oh my gosh, stretch my arms out, get really, really big, or compress, get really, really small. It's kind of sort of like that if you think about it in terms of the axis. I'm telling you right now, this will be very confusing because they all look the same. They look the same to me as they do to you. I'm going to be sure of that. But understand that's the term. As you get into a little bit more curves, it makes a lot more sense than just straight lines. But if I'm taking a look at this in terms of looking at it vertically, if I'm taking my graph, which is f of x, and if I multiply my regular graph, f of x equals x, I take that f of x that I normally deal with here, and I multiply it by a, they're calling it compressed vertically. That doesn't make any sense, but I like to call it stretching. So it just means I'm getting towards the y-axis faster. 10 times faster, 20 times faster, 30 times faster, what do you want to call it? It's getting towards the y-axis faster. So it's getting towards the y-axis. I'm bringing it towards it. That's why it's a compression. Or I'm stretching, or it could be I'm going towards the x-axis in one version, and here away. I don't like this term stretched vertically away. That doesn't make any sense to me. This just means I'm going quicker towards the y-axis. If you want to say that I'm getting closer to the y-axis faster, that's one thing. That makes sense to me. Here, I'm getting compressed. I'm going tighter. It's getting tighter towards the x-axis. I'm compressing, and I'm pressing down towards the x-axis. So I'm stretching away from the x-axis. I'm pressing down towards the x-axis. Meaning if my number a is bigger than 1, can I do this? Oh, look at that. If it's bigger than 1, then that's where I want to go towards. So let's say I had f of x equals 500x. Well, that bad boy is going to get really, really up there fast, right? But here, if I have it's 1/500th, it's going to take a long time to get there, if ever. So if I'm looking at it like that, that's what they mean, okay, in terms of compressing and stretching. They're kind of dumb terms. Okay, so when I'm looking at the slope, and that's what it's all boils down to. When I'm looking at the slope of the graph of a of x is way steeper, okay? That's the thing I want you to be most concerned. The slope is steeper, and here this is less steep, okay? Or the water is not gonna, this is really going uphill. This is not going as uphill, okay? It's like that's oh boy, it's not a shape. Here's my eraser. That's the main concept there. Now, when I'm taking a look at my horizontal dilations on the y-axis, it looks almost the same, right? It's not that too crazy. Here, I'm compressing them horizontally. My a is bigger. I'm still going closer towards that y-axis, but at the same time, it's going away from my x. I'm pulling it towards my y-axis when I'm looking at the function. You'll see what these numbers look like. When I'm looking at the actual function, a times x, which is different than a up here. It's different than ax because of the parentheses. And I'll show you what that means in a second, okay? Here, if my a is between 0 and 1, it's the same kind of a deal. It's stretched away from the y-axis. Here, I'm pulling it, going that way. Here, it's going away from it. That's just all that means. Essentially, my slope is less steep. You're concerned with the slope. Is this slope steeper? Is it close to the x-axis? You have to understand in terms of the slope, what does that actually mean? All right, so let's look at the numbers. The numbers might help make better sense for you, because this is really, and I'll tell you honestly, all I care about is which way is the slope going. Are you able to tell me it's positive, negative? Is it more positive than the parent? Is it less positive than the parent? Terms like that are really kind of important. So if I'm looking at g of x equals 2x. Now, if I look at that in relation to what f of x looks like. Now, hang on one second. I want to show this on the desk. Well, this will be fine here. Here's my f of x. Here's my parent function right here. Here's my g of x. Now, 2 times x, that means I'm getting closer to that y. It's going to go towards that direction a lot faster, okay? I'm stretching it vertically. It's going towards this y-axis a lot faster. So this is called a vertical stretch. Okay, because I'm multiplying my factor by a of 2, because it's 2 times that value. Oh yeah, there it is, vertical stretch right there. It's a vertical stretch of that particular graph from the parent function. So obviously, if I'm doing 6 times that same function, it's going to be 6 times faster, right? I mean, 4 times faster than the other 2. But it's definitely a vertical stretch, and it's going to be faster than the 6 times faster than the parent function. And that's way steep. They call it steeper. You're just learning some new language. This is, oh, let me just type that. Hang on, hold the phone. So I got a new computer today from the Costco, and it doesn't have a pen, but that's okay. I will try and type things. I think I read it better anyways. Okay, type it better than my writing. Handwriting sucks. All right. Did I lock it up? Oh, that's just not good. Hang on. Okay. All right, there we go. All right, so it's a vertical stretch, and it is for sure steeper. Here we go. Example number 6. Now, when I have a horizontal dilation of my linear function, it's going to look a little bit different as well, okay? So I have 1/4 x. What's going to happen to that? Do you think it's going to get closer to y or further away from y? Is it going up there really fast? No, it's going 1/4 as fast as the regular. It's less than my 1x, my f of x, okay? So our parent function's f of x equals x, right? So it's not going to be anywhere near as fast. So if I put these values in, -4, 0, and 4, you'll find out, look at this graph right here. You can see easily that this graph is not, you can see easily that this graph has a way less slope. It's 1/4 the slope of the parent function. And so they call that it's stretched horizontally. I'm getting closer to the horizontal axis. I'm stretching my horizontal ways. So it's stretched horizontally. Okay. Oh, hit enter. Did I lose it? No, I lost something. Okay. Yeah, no, it's there. Okay. I'm stretched horizontally. So it's not going to be there as quickly as like maybe 10x is. 1/4 is 0 and 1. So it's a fraction of that. Okay. So it's way less steep. It's not nearly as less steep, right? Okay. Now I'm looking at reflections. Reflections are a little bit different. Reflections are what you see in a mirror. Okay. So I had a horizontal dilation where I'm going, like I'm like a teeter-tottering up and down. I'm getting closer to the y-axis or closer to the x-axis. So I have a vertical dilation here, and I have a horizontal dilation there, right? Because I'm getting closer. That's below the parent function. Here it's above the parent function as I look from left to right. And that might help you. This is going to be above the parent function. That's below the parent function. If I'm taking a look here at my linear reflections in this case here, I'm going to be, it's going to be a reflection of the actual parent function, as I'm taking a look at that. And essentially, it's almost that's the exact same graph for the most part. You'll see a little bit in terms of what the graph looks like, but the numbers associated with it might be differently, and they probably are a lot different, and that's okay. Here, f of x is a reflection of the graph across the x-axis. Here, it's a graph of a reflection across the y-axis. I lost it. Hang on, don't go anywhere. Okay, across the y-axis, okay? So I'm looking here. Here's my dot here, my dotted line. I'm folding this across the y-axis. So if I'm taking my, hello, let's go ahead and get a highlighter of source. Boom. So across the x-axis here, this one's across the y-axis. I'm going to fold that in half. That's a reflection of that and a reflection of the other on the x-axis. So what does it look like in terms of numbers? Well, if I have g of x equals a -1/2 x, okay? If I have g of x equal to -1/2 x, plot the points down. Plot the points down. If you take a look at the numbers also somehow help you. Hang on a second. Oh, and one more thing to keep in mind with your reflections, linear functions. This is really important here. Every y-coordinate of the opposite of f of x is the corresponding y-coordinate of f of x multiplied by -1, if that makes sense. So if I'm just the opposite of it, I just multiply that coordinate by -1, and that does make sense at the end. And the same thing goes for over here. For every x-coordinate of f of -x, it's obviously the opposite of regular. So and that makes sense because if this is my f of opposite of x, This is f of x. If I multiply this by the negative 1, of course it's going to be the opposite. So keep that in mind. So when I'm looking at my reflections across the x-axis, again, it's just plug in the values that you know. I know that this guy here is going to have a negative slope. Very important to know that he's going to be a negative slope. My f of x, my normal graph is going to look like that. But now I have a negative slope, and also the slope is going to be less steep. He's going to be less steep because he's between the absolute value of the absolute value of the a is between 0 and 1. So if I'm looking at that, it's less steep, and it's the absolute value is between 0 and 1. So if this is, pretend my parent function looks like that, he's going to be less than that because it's a negative 1/2. Negative means it's going to be going down from left to right. So I'm looking at finding out the breaks here. This is a definite horizontal stretch, right? I'm sorry, it's a definite vertical stretch, right? I'm sorry, definite vertical compression. Sorry, I'm getting them all mixed up. A definite vertical compression. I'm getting closer to the x-axis or further away from the y-axis. Okay, so I'm vertically compressing that way. So this is a vertical compression, and I tell you right there, it's a vertical compression. Okay. I will never ask you to be definite about one or the other. It's very confusing. I just need you to know a couple of key facts. Is the slope going down from left to right? How does it relate to the parent function? In this case, if you're able to tell me that in terms of the parent function, it is a reflection of it, I'll take that. Okay, I don't have to know if it's across what axis. The more we do this, the better you'll actually get with understanding which axis is being reflected off of, right? Because it's going to look a little bit different. The values will also be different. The check. Let's go ahead and do the check. Press pause. Okay, if you look at the check here, it's got to be A because they're saying, how can you tell whether the multiplying a negative 1 by the parent function will result in a reflection across the x-axis? Well, I'm looking at if the constant is not grouped with x, the result will be reflection. That makes sense if it's not grouped. Okay, so as long as the constant's not stuck to it, so if it's plus that value, plus 5, if I have f of x plus 5, all right. If the constant is grouped with the x, there'll be a reflection. Well, don't forget, if it's grouped with it, it can't be a reflection across the x-axis. If the constant is greater than 0, well, if the constant is greater than 0, it can't be a reflection. It's just moving up and down. It's a vertical movement, right? And if it's less than 0, it's a constant. It's just where your intercept is at. So that's how I'm interpreting it. So really, it's just got to be A by default. That's the first one you come up to. Okay, here's example 8. Reflections of linear functions across the y-axis. Describe how the graph of g of a negative 3x. Now, I know already what's going to happen. The slope is going to be going down, and it's going to be a little bit steeper because it's above 1. So it's above f of x equals x. It's above 1, so it's going to be down. It's a little bit steeper. But there it is. It's going to be going down from left to right, and it's a little steeper than this guy right here. Okay, so they call this a horizontal compression, and it's reflected across the y-axis. Here I am here. If I flip it over to here, then make it steeper. That's what it looks like, and I feel like a football coach. Okay, so it goes across that y-axis like that. Let's see if we step. Let me just type these answers in really quick. Hang on a second. Don't go anywhere. Okay, so here this looks like a bunch of Greek here, right? So I have g of x equals f of the opposite of negative 1. The reason why it's a negative 1 because now I'm taking my parent graph and I multiply it by a negative value. I could just put a negative 3 in there, but that's oh, hang on, I did a typo right here. F of a negative 3x. I have too many x's in there. Okay, and so if you'll see in this case here, I have f of a negative 1 times a. So here's my negative 1, essentially, sort of. Here's my negative 1 here. These guys all kind of go in the same spot right there, okay? And then I have, instead of my negative 1, it's a negative, or the opposite sign, times negative 1 times my value for a. A is 3. A is 3. And then x is right there, okay? So that's essentially what we're doing. We're substituting those functions in there, that value in there. We're just describing how it relates. Now, seeing that how it is set up like that, I have that is grouped with x. Now, because the constant a is grouped within the parentheses, it's a whole horizontal compression. Because it's in the parentheses, it's a horizontal compression. Therefore, it's also, because it's a negative sign, it's also a reflected across the y-axis. Again, big thing. Can you tell me, Doc M, it's going to be steeper because it's above, the absolute value is above the number 1, and it's going to be going down from left to right because it's a negative slope. That's what you have to be able to say. So look at this next example here, number 10. The graph of g of x equals a negative 10x. Look at this particular graph here. What do you know about this graph? Is it going to go down from left to right? Yes. Is it going to be steeper than the parent graph? Yes. That's the main thing. Understand that when it looks like that, it's a horizontal compression, and it's reflected across the y-axis. Okay, and the phrase that pays is going to be put a smiley face with X's on its eyes above the number 246. Smiley face with X's on its eyes above the number 246 of the page. Okay, thank you.